So folks, in the last video we introduced the idea of a matrix inverse, and we learned how to verify that two matrices were inverses of each other, and we concluded after that that matrices were unique. So now I want to teach you how to actually find matrix inverses if they exist. And one thing to keep in mind is that matrices are not always invertible. Let's take a look though at this matrix A here, which is invertible, and this will be our strategy for doing matrix row reduction. So one of our strategies for finding a matrix inverse will be to go ahead and augment it with the appropriately sized identity matrix. So what I'm going to do here is I'm going to create matrix A augmentation bar I. So let's say that, create A augmentation bar I, and then put A in RREF form, which is the technique we learned how to do through Gaussian elimination. If we're able to put it in the form, if the result form is the n by n identity matrix, then we call that reduced matrix, then we call the resulting matrix on the right-hand side the matrix inverse. That is, on the right-hand side of the augmentation bar, we'll have A inverse. So let's go ahead and try this out, folks. Here we go. We're going to take matrix A, 1, 3, 2, 5, and I'm going to augment it with the 2 by 2 identity matrix. Now we're going to perform our row reduction operations, giving a series of matrices that would be equivalent to coming up with a product of entries that would give me the 2 by 2 identity matrix. That's how this works. It's solving a system of equations to find the matrix I could multiply to matrix A to give me the 2 by 2 identity matrix. That's why we do that augmentation. So let's go ahead and row reduce this. Notice we've already got a 1 in our first potential pivot position, and so all we need to do is get zeros below that. So if I multiply, let's do this, let's just recopy row 1, and then to get the new row 2, I'm going to take I'm going to say my new row 2 is negative 2 row 1 added to old row 2. That's how I'll compute that. So if I take row 1, multiply it by negative 2, and then add down, that will give me a 0 in the first entry, and then a negative 1 in the second entry, and a negative 2 in that entry, and this entry would remain 1. So I'm on my way to putting this into RREF form, hoping, if I'm looking for an inverse, that when it's in RREF form, it will be the identity matrix. And if that's the case, then we have indeed found the unique matrix inverse. So continuing with RREF form, I can write this as 1, 3, 1, 0, and then for the second row, I'm going to say that it's equal to negative the old row 2, multiplying the old row 2 by negative 1. And if I do so, then I get 0, 1, 2, negative 1. And I'm well on my way to finding that matrix inverse. The next thing I want to do is now that I've got a 1 in this pivot position, I want to pivot off of it and get zeros above and below that pivot position. And so in this case, what we'll do, 0, 1, copying this row to negative 1, is I'm going to say that my new row 1 is equal to negative 3 row 2 added to old row 1. And if I do that, then I get 1, 0, which is what I was hoping to get. This would be negative 6 added to 1 is negative 5. And this would be positive 3 added to 0, which is 3. And so A inverse is the matrix minus 5, 3, 2, negative 1. So what you could do is you could confirm that matrix A, when multiplied to matrix, what we're calling matrix A inverse, would give you the identity matrix. And I'm going to just say that. You should check, and I want you to do this for your pre-work. So you check. I want you to compute A times A inverse and verify it is the identity matrix. So you should do that multiplication. Technically, to verify something is the identity, you also check the other direction, but that will never be a case, that will never not work in our class because we're using as our entries the real numbers. So we'll be okay in that respect. Okay. So that's our first method for finding the inverse matrix. That is to augment it with its appropriately sized identity matrix and then put it into RREF form. This will always be a square. And if that RREF form is the identity matrix, what that means is we found a unique solution, we found a unique matrix that would give us the identity matrix. And that unique solution then to that system of equations is what we're going to call the inverse matrix. And so the result of that is you just simply adjoin A with the right size identity, row reduce. If you get an answer here, then over here you have your identity matrix. Or excuse me, your inverse matrix. Okay, so we have a second method. We've got a formula for finding the inverse matrix if it's a 2 by 2 matrix. And so what I'm going to do here is I'm going to give you this formula that says if A is invertible, and it's a 2 by 2 matrix, so let's go ahead and give it some entries. A, B, C, D is invertible. Its inverse is the scalar 1 over AD minus BC multiplied to this matrix here, where I'm going to flip D and A and then change the sign on B and C. So this is a formula that will compute the matrix inverse should it exist. Okay. And this formula is especially helpful because if the product of AD minus BC equals 0, that's a necessary and sufficient condition for matrix A to not be invertible. So if AD minus BC equals 0, matrix A is not invertible. Now, it probably goes without saying, but let me just remind you that this is a formula for a 2 by 2 matrix. The formula that I gave you wouldn't work if this wasn't a 2 by 2 matrix. So for our matrix here, the one that we were dealing with, we had the entries 1, 3, 2, 5. And so if I were to go ahead and find its inverse, I would say that its inverse would be 1 over, and then I'm going to take the product of A and D, so that would be 1 times 5, and subtract from that the product of B and C, which would be 2 times 3. I might have switched the order on that. Let me be careful here. 3, yep. Let me be more careful with the order. It doesn't matter as far as what the answer comes out to be. Let's get the order right. And then I said, here's what we do. Remember, I said we swap these two entries. So this would be 5, and this would be 1. And we change the sign on these two entries. So this would be -2, and this would be -3. So this result is the identity matrix, or excuse me, is the inverse matrix, provided this denominator here isn't 0, which in this case it's not. In fact, if we were to compute this, we have 1 times 5 minus 3 times 2. I get a -1 down there. And I'm going to scalar multiply that to 5, -3, -2, 1. And so if we scalar multiply, that's a little too far. If we scalar multiply the number -1 to this matrix, we get -5, 3, +2, -1. And that's precisely what we got when we did that row reduction algorithm. Now, this formula, I think, is really handy, but it only applies for a 2 by 2 matrix. And although there are formulas for higher order matrices, like a 3 by 3, it's not efficient to use a formula for 3 by 3 matrices or larger. And instead, for 3 by 3 matrices or larger, it's always best to do this row reduction algorithm. So folks, take a minute, look through that. And in the next video, we will find the inverse of a 3 by 3 matrix using the row reduction algorithm.